topic. Since today is examination, so I'm not going to do tough problems today, because the topic which will be covered in today's class, it is not there in the examination. So therefore, let us discuss something which you will find very soothing, okay, for today's class, because I know you are mentally, you are in a mental pressure for the examination. I shall first talk about this star, which was the operation that was defined on the set, to make the set, was defined on the set to make the set group. I will talk about this star, and I will give a formal definition of this star only. So what is star? What is this? This is the question. So the definition of this binary composition goes like this. Okay, let capital A be a non-empty set. Be a non-empty set. Okay, let capital A be a non-empty set. A binary operation, star on A, binary operation star on A is a function. A binary operation star on A is a function from A cross A into A. Okay, so this is the actual definition of the binary composition which was defined on the set to make it group. Say for example, if I take a set of natural number, and if I define a binary operation, say plus, as you know, the binary operation is a function and its domain is the set A cross A. So I'm defining the function. We used to write a function in this manner, f colon A to B. As you can recall, you have learned it in school days. So I am defining the function. In place of f, I'm putting plus. Now just consider this to be a function. Okay, the symbol in place of f, I have used the symbol plus only. In place of A, I am taking the Cartesian product of the set of natural numbers n cross n, and I am defining this function from n cross n to n. So what does it mean? It means that if I choose any pair from n cross n, say for example A comma B, and if I apply the plus on it, we actually get their sum, which is denoted by A plus B. And you can write this sum as another natural number, which is C. Actually, in school, we used to learn in the following manner. We learn addition of two natural numbers, and we know that the sum of two natural number is a natural number. But when you are adults and you are in higher mathematics, we always try to generalize the things. We always try to visualize the same old thing from a different perspective. And therefore, this is the perspective which I am showing to you right now. Okay, this is one of the examples of binary operation, which is generally denoted by star. So it is my example number 1. Another example I'm writing over here, example number 2. It could have been nice if I could have written this in below the definition. Anyways, example number 2 is suppose I consider a set of integers z, which is a set of integer. It is a set of natural number. a set of integers. And if I define a binary operation in this following manner, in place of f, I'm writing max. So max goes from z cross z to z. Okay. Then we define this max in the following manner. We define it by, if I choose two integers, small z1 and small z2, say, then we get an integer which is either of these two. This result can be either z1 or z2, as the case may be. So I can write it in the following manner. So I can write it in this manner, m of z, and let us not write m because my function, the notation for my function is max. So let us write max. Max of z1 and z2 will be z1 if z1 greater than z2, and z2 if z2 greater than z1. Okay. This max is also an example of binary operation. This plus is an example of binary operation. This multiplication sign is an example of binary operation. Division is a binary operation. Minimum of two elements is a binary operation. You can in this particular manner, you can consider any operation, you can design any operation which is binary operation. So basically, binary operation is a kind of function which connects two numbers, and therefore it is called binary. It connects two numbers and it tries to form a single number. Here plus is trying to connect two numbers a and b. Here max is trying to connect two numbers z1 and z2, and their result, their outcome is a single number. And therefore it is written, it is a binary function from a cross a into a. Okay. So this is the definition. This is the actual definition of binary operation. Now this binary operation may have various characteristics, you know. Now let us write, I can say that, suppose this is my definition 1. Okay. My definition 2 is the following. What is the definition 2? Now suppose, let capital X, comma star, okay, before that I must write that this one, a mathematical system or let us write by a mathematical system, we actually mean an ordered n plus 1 tuple x, comma star 1 star 2 dot 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 star 3, where x is a non-empty set, and star I is a binary operation, on x. I is equal to 1, 2, 3, dot dot dot, n. Okay. So this type of system where we actually consider a non-empty set and we design various binary operations, on the set capital X. This type of system, when written together, they are called, this is called a mathematical system. This is actually the definition of mathematical system. When we talk about, many people have, probably many of you have encountered this word mathematical system. Let us deal with a mathematical system. So what is the definition of mathematical system? In mathematical system, we need a non-empty set. We need several binary operations in general, which will be defined on X. So if you ask me to give you one such example, so I'll say that, okay, let us consider, for example, let V is a non-empty set. Let V is a non-empty set. And we define vector addition. And scalar multiplication on V. Vector addition and scalar multiplication on V. And you already know that the triplet V plus dot, we define this addition by the notation plus, and we define the scalar multiplication by the notation dot. So V plus dot, this triplet, you know, is a vector space. You have learned it in your first semester course with some properties to be satisfied. You already know this. And yesterday I told you that let capital G be a non-empty set, and let us define a operation star in general. Okay, and with some properties, this is called a group. So we learned vector space earlier. We learned, yes, in the last class we learned group. So you see, this is a triplet, this is a pair. In this triplet, we have a non-empty set, 2 operations. In this pair, we have a non-empty set, 1 operation. So both of these things are actually 2 different types of mathematical systems. Okay, and these are not the only mathematical system which we have. Apart from these, other mathematical systems are also there. Okay, so when we have two things inside the bracket, we call it pair. When we have 3 things inside the bracket, we call it triplet. But when we have more than 3 things, when we have 4 things, we call it quadruple. But when we have more than 4 things inside the bracket, we call it tuple. We use the word tuple. Okay, but why it is n plus 1 tuple? It is because we have considered, sorry, this is n. We have considered n binary operations, star 1, star 2, star n. Each of these binary operations is defined on capital X. So how many binary operations are there? N binary operations are there. So n elements, n items are present over there. 1 extra item is also present, which is the non-empty set X. And therefore it is called n plus 1 tuple and not n tuple. And why this word ordered is written over here? Why? What will be the problem if we do not write the word order? Okay, let me try to explain that. Suppose one of you have considered the set of say for example, okay, so the set of integers, let us consider, and he is defining the set of integers he is considering, and he is defining the binary operation minus from z cross z to z by minus when operated on 2 elements a, b, is giving you the quantity a minus b. Now, if he designed this binary operation in the following manner, then what will happen? Suppose he is choosing, for instance, he is choosing a is equal to 1 and b is equal to 2. Then, according to his definition, 1, 2 will be 1 minus 2, which is minus 1. But this minus 1 is not equal to 1, which is actually the result when the binary operation minus is operated on 2, 1. Now you see this 0.12 and this 0.21, these are not the same ordered pair. If you think about the coordinate system, 0.12 will be, this point is 1, this point is say 2. So 0.12 will be this point. And if you consider 2, 1, then that point will be this point. So these are the two different points on the Cartesian plane. So if you do not write the word ordered, then there will be some trouble, because if we change the order, or you can say the positions of the two elements, then when the binary operation act on it, their outcome is not same. But this is not happening in case of multiplication, and this is not happening in case of addition, but this is happening in case of subtraction. This will happen in case of division. Okay, so without any loss of generality, to generalize the thing, we have to use the term ordered over here. So to define a mathematical system, if you do not use the word ordered, then your definition of the term mathematical system is not complete, and therefore this word is very significant. You cannot avoid it. By the by, I can see there are 70 participants, including me. So actually there are 69 participants, but only 66 participants have put their attendance. I think 1 or 2 participants are there who haven't written their roll numbers in the chat box. Okay, so I'm just reminding you, later you just don't tell me that you have forgotten to put your attendance. So this is the thing which this is the this is the reason for which actually this word ordered is actually written. Now I'm going to write my definition 3. The definition 3 goes like this. Let me change my color. Okay. Let capital X comma star be a mathematical system. Now probably you have understood why have I written the definition 2? Because first of all, you have to know what do we mean by mathematical system. So let X star be a mathematical system of a single binary operation. Single binary operation means only one operation has been defined, that is star. Okay. Then number 1, star is called associative. Star is called associative if for all X comma Y comma Z in X, we have just a minute, it is not, I'm unable to erase it, just a minute. X star Y star Z, this should be equal to X star Y star Z. And number 2 is star is commutative. Star is commutative if for all X comma Y in capital X, we have X star Y is equal to Y star X. Okay, this is the meaning of the terms associative and commutative, which I used in my last class. Now you may think, some of you may think that sir is taking a bit amount of time to explain the terms which we already know. But no, hold on. Yesterday when I gave a problem, on the to show that a particular structure is group or not. One of the students actually, I think, was confused about these things, about this definition: x star y star z is equal to x star y star z. He couldn't associate the thing properly, and there he actually made a mistake, and he told me that the thing was not associative when it was actually. So the thing which I'm now explaining to you may look very simple to you, but these simple things often become so complicated if you do not put attention. And since I'm asking all the CSE students that I know that you are in computer science and engineering, you are going to work in a software company, and suppose you are involved in a kind of research work, or you are involved in this kind of designing something. Okay, so some circuits or etc. You need logic gates and like AND gates, NOR gates, and Boolean algebra is so important for you. So all these studies are actually will be helpful if you do it properly. Say for example, I can say that say for example, this word for all, if you miss this word, then there will be trouble. This for all, these words which I have written over here, they are very significant. You have a topic called mathematical logic, where these terms like for all, for some, there exist, or and negation, that those things will be studied. So every chapter of your syllabus of your course curriculum of PCCCS 401 are interconnected to one another. Okay. So yesterday I gave you the definition of group without explaining the things properly. So today I have decided, okay, let's explain the thing properly. Let's explain what is binary operation, then let's explain what is mathematical system, and then let's explain what is associativity and commutativity. So you'll understand what we actually mean. Okay. Mean by them. We need to know the definition. Now I'm giving a definition which you will probably now understand, and you will be able to correlate this with my earlier study. The definition is definition number 4. It goes like this. So I'm now writing it in black color. A semi-group is a mathematical system. A semi-group is a mathematical system. A semi-group is a mathematical system, A star, where capital S is a non-empty set. Capital S is a non-empty set, and star is an associative binary operation. Associative binary operation on capital S. That is A star B star C. This is equal to A star B star C. For all ABC, this word for all is important. For all ABC belonging to capital S. Now you see, just look at this definition. Just look at this definition, what I have written. Every word, every single word, like mathematical system, non-empty set, associative, binary operation, I'm marking them. Let us mark it. This word, associative, binary operation, every single word is actually clear to you. You know definition of each and every word, and therefore you will never forget the definition of semi. Only one new term has been introduced over here, which is called the semi-group. So in group, they actually satisfied the structure actually satisfied 4 properties. Semi-group is a smaller structure. It's also a structure, it's also a mathematical system, a smaller mathematical system which only satisfies one single property, that associativity is satisfied. And there are structures like this where the thing is only associative. Okay, semi-groups are the examples of semi-groups are there. Okay. Now I'm going to the next page. It would be nice if you take a screenshot of this pages that I have written. Take a screenshot. This is my page 1. This is my page 1 of today's class. Take a screenshot, and this is my page 2. Okay. Take a screenshot. I hope you have done it. So I'm going to the next page to give you some more extra definitions. So today's first session is actually built upon definitions. Know the definitions. If you know the definitions, you know the system. Okay. When you forget something, when you are unable to do a kind of mathematics, but how will you solve it? You will go back to the definition. You will go back to the definition and you will try to rebuild the entire thinking process so that you come to a conclusion. But if you forget the definition, then that problem will never be solved by you. Now, another definition I'm going to give you. The definition goes like this. That will be definition 5. An element small a belonging to capital S. It is talking about a single element, small a belonging to S, is called idempotent. Idempotent. You are not unfamiliar with this term. You have got it in case of matrix theory. You have learned the idempotent matrix. If A star A is equal to A star A is equal to A. Okay, so in matrix theory, the idempotent matrix are those, the idempotent matrix is that matrix A where A square becomes capital A. A simple example is the identity matrix. Identity matrix is the idempotent matrix. So in general, this is the definition. This is the definition when we call that a particular element is idempotent. Now, a semi-group S star, semi-group you have already defined. Semi-group is that mathematical system where the binary operation star is only associative. A semi-group S star is commutative. That is a semi-group S star is commutative if the binary operation star is commutative. The semi-group will be commutative if the binary operation star is commutative. That is, A star B is equal to B star A for all A comma B belonging to capital S. I hope you have understood this. Otherwise, it is called non-commutative. Otherwise, it is called non-commutative. Okay. Now, the important part, I'm putting a star mark over here. If the semi-group if the semi group, that is, I hope that if it would be nice if I put another definition number over here. If the semi group has an identity element, if a semi group has an identity element, okay, then such a mathematical system, is called, such a mathematical system is called monoid. Such a mathematical system is called monoid. So for example, if I consider, say, Z plus union 0, set of all positive integers with union 0, which is sometimes given by this, okay, in this manner. In some books they call it positive whole numbers. In some books Z minus is called negative whole numbers. In some books you may find that the entire set of integers is called the whole numbers, positive and negative including 0. So I'm considering non-negative whole numbers and define plus on Z plus union 0. Then you see that this Z plus union 0, let us call this Z plus union 0 as, let us denote this by Z1, okay, for simplicity, Z1. Now you see that Z1 under the operation of addition plus is actually associative. It is actually associative, and the identity element, 0 is in Z1, So by above discussion, we can say that by above discussion, we say that since Z1 is associative with respect to addition, so Z1 plus is a semi-group, and as 0 belonging to Z1, so, and 0 is the identity element, so Z1 is also an example of monoid. And you can design many such examples of monoid, okay, other than this. I have just given you an example of monoid, a structure. Now you can take, this is my page 3, you can take a screenshot of this particular page, okay? And my time is also running out, so I think I have to stop here, and in the next session I'm going to continue with my further discussion on the remaining topics, okay? So in today's class we have first learned that what we mean by binary operation, what we actually mean by binary operation. And yesterday I called this as binary relation. Now relation and operation and function, all these terms are to some extent synonymous, okay? So I have not formally taught you function in the class, but when I'll do so, I will connect all these words, relations, functions, operations together. Then you are going to understand what I actually mean. Now this binary operation has been defined. First of all, I have given you examples of binary operation. This is the first example, this is the second example. Then I told you that what do you actually mean by mathematical system? Many a times we have used this word, let us deal with the mathematical system. We also say that let us deal with the physical system. What is the definition of physical system, mathematical system? Definition is very important. After that, I gave you the definition of the binary operation being associative and commutative. Then I discussed what do we mean by semi-group, which is a smaller structure than group. Idempotent element was defined. Okay, and when we call a semi-group to be commutative, that has been explained. And semi-group, and also we have explained when we call a semi-group to be a monoid. So you have to remember each and every definition written in these 3 pages. So I'm stopping here right now. Let's join in the next.